All right, so this is chapter 30, atomic physics. Repeat for those of you who weren't paying attention. So remember, you should be able to look at the chart and be able to know which number is the atomic mass and which number is the atomic number. So this one is the mass, which is also known as the letter A, and this one is the atomic number, which is also Z. And so Z represents the number of protons. Atomic mass is the protons plus the neutrons. So if you do A minus Z, you get the number of neutrons. So if you see 238 uranium, you know that there's 92 protons, 92 electrons, and 238 minus 92, which gives you 146 neutrons. That's the easy part. This part's not super important, but you should sort of, in general, know that Thomson started with the plum pudding model, and everything was all mixed together. Rutherford decided that there was a really big nucleus in the center. Bohr's the one that we pay attention to. This is the one we use, but when we use this one, it's not quite right, but it works for us theoretically. So that looks like a solar system, and so each of those circles represents an end shell, and the electrons stay in that circular orbit, and they can only have a certain number of electrons and all of that. And you excite them from one level to the next level, and that's how you get energy or release energy. These two, de Broglie and Planck, are what we know as quantum. And that's where things get a little crazy, where they have stable orbits that are integer multiples of some standing wave, and that Planck said that these are whole number integers of h, and now the orbitals look more like this rather than like this. So this is Bohr, and this is quantum, and it gets a little crazy, right? And they can be, notice they can be in the center, even when they're not in the first orbit. What's his name? Sorry. Planck. Schrödinger said that there were these clouds, so this is probability, so it can be everywhere. So not only is it just making these strange shapes, right, which we had but now we also know that Schrödinger, that's over his name, said that they can be anywhere at any time. So it doesn't matter if they're way out here. Every once in a while, they can be in the center and have a lot more potential energy because they're closer than they were before. So for light emission, it's the difference between the orbitals that gives you the energy of the photon. We know the energy of a photon, so this is energy of a photon, is equal to HF. And so you can calculate that by looking at that energy difference. We know that electrons stored further from the nucleus have more stored energy, right, because of potential energy. So that's my electrical potential energy type of energy. This is the chemistry model, right, where we can say 1 over lambda is equal to RZ squared 1 over N1 squared minus 1 over N2 squared. It's not so much for physics, but it still gives you the energy, right? So because in some form you got 1 over lambda, and we know that HC over lambda is energy. And so you can figure it out from this. Rydberg's constant will not be given to you at any point, but it's just 1 times 10 to the 7th. And so this is just showing you pictures. These are supposed to be the photons coming out as the electron drops from one orbital to the next orbital. So this one is going to have higher energy, so it shows it with a bigger frequency, and this one, because it has a smaller jump, is going to have a bigger wavelength. It has a smaller jump. Remember, the further out you go, the tinier and tinier the jumps get as well. Not as evident in that picture. This one, it looks better. You can see up here, very small difference of energies as you get further and further up. Here's the big one, and that one is our Lyman series, which gives us UV. And then if you jump in this area and above, you're starting to get into the visible, and then passion is even less energy when you're only jumping in here. So it gets smaller and smaller energy. Remember, if there's an N1 involved, it's Lyman because of this huge jump, right? It doesn't matter if it jumps from here to here, or here to here. As long as it makes through that big jump, it's going to have a lot of energy. Whereas with Balmer, right, the jump can be anywhere in here, and they're just smaller jumps, so it's less energy, so we get visible light. And then for passion, you get tiny little jumps right there, right? So that's not going to be much energy, so now you're in the infrared. You can either absorb, right, or release, depends on which way you go. So if I go down, then it's releasing energy, and if I go up, then it's absorbing energy, right, because it has to go up. And it only does that in H increments, right? It can't just do anything. So if you only give it a little bit of energy, it's not going to go oops and come back. It's just not going to go anywhere, and it's stuck. So it has to have the minimum energy to get to number 2, and then the minimum energy to get to 3. Also, when it's jumping, it can jump in series, right? So it can jump from 4 to 1, or it can jump from 4 to 2. That's okay. So you can get different amounts of energy photons coming off. When you're trying to figure out the energy of an orbital, we use physics, which doesn't quite work, but at least conceptually it makes sense. So Fc is equal to Fe. So we know Fc is mv squared over r. This is Coulomb, right? It looks like Coulomb, right? Q over r squared. It's just that QE is equal to the charge of an electron, and the Z is the number of electrons. And so if I put that together, I end up with ZE squared over r squared. And then if I do a little math, right, one of the r's cancels. And so I'm left with mv squared over kze squared over r. So that means that mv squared is the same as this. So when I'm looking at the total energy, which is ke plus electrical potential energy, it's 1/2 mv squared plus EPE. Well, EPE is still kq over r squared. And now for the mv squared, I plug that in here with a 1/2 in front of it. And so you end up with kze squared. So basically, if you're looking at it, the kinetic energy, if you think about it, is equal to half the electrical potential energy, right? Just according to the equation that we have. Kind of interesting, I think. And then we have angular momentum of an electron in the Bohr atom. So we know that L is equal to I omega, and we know I is mr squared because you just have one thing spinning around, and so it's got an r, and so that means that it's basically mr squared. Remember, you could have 1/2 mr squared and all those things. Then when you solve it, you end up with mvr, and so you end up with, for Bohr, every nh over 2 pi is equal to mvr of the nth orbital. And so that means that L is proportional to n, right? And since n cannot equal 0, L cannot equal 0, right? That's the big takeaway. Then this is just a whole bunch of comparisons, so to speak. So you can see that the radius of the orbital is directly dependent upon n, which makes sense, and inversely proportional to z, which also makes sense because it's going to have more protons pulling it in. Again, concepts more than the numbers. The energy of an atom, this is the electrical potential energy, it's the total energy, right, because we got the 2 in it. So it's kze squared over 2r. So that's the total energy if we compare kinetic energy and potential energy. Then we have the energy of the nth orbital, which again is inversely proportional. Well, not again, it's backwards, right? So it's directly proportional to z squared and inversely proportional to n, right? So as you have more z's, right, more charge, you can have more energy. And as you get further away, you have less ionization energy because that's the negative one. And then this is also, so these two, just so we know, is ionization energy, right? How hard it is to pull it away, as opposed to the total energy of the atom that it contains, which is electrical potential energy plus kinetic energy, right? Gets a little confusing. But the further out you get, the less hard it is to take it away. You should remember what your electron volts is, and that is 1 joule per coulomb, and 1 electron volt equals 1.6 times 10 to the negative 19th joules. And when you go to infinity, energy goes to infinity because it's easier to get out. Big takeaway. I think that's the big takeaway from this. Here is the picture kind of showing the ionization energy is equal to E infinity. E at infinity, remember, is always equal to 0. So that's why you have these negative numbers, because it takes 13.8 electron volts to pull it out there, 3.4 to pull it out there, right? And 0 when you get far enough away. It's basically the same equation as the Rydberg equation, but to me this one makes more sense because I can think of it with physics. For quantum mechanics, remember, electrons do not stay in the orbit. They're all over the place, so this is the most likely place for it to be. So they can't be assigned to one orbital number like n, like the Bohr uses. Instead, there's 4 quantum numbers to describe the electron's position and motion in the atom, and no two electrons, can ever be in the same place in the atom. So the 4 quantum numbers, remember we talked about, we have n, which is the principal quantum number, which can be 1, 2, 3, blah, 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 shells. And then you can see, remember that was the K shell when we were going to the K shell for the problem. You have more shielding just because you have more in between it, right? So there's a K shell, an L shell, an M shell, an N shell. I don't think they're going to ask you if you know what the letters are, but just so that you know that they exist when they talk about it. The L is basically the shape of the orbital, right? So you have the S, which is a circle, and then you have the P's that kind of look like circles. But remember, you have like more of those that go like that, which work much better with balloons. And then you have the D ones that kind of look like that, and they have like a donut in between. So those are S, P, D, F, G, H. Remember, I was trying to do that as A, B, C, D, F, G. That doesn't work. So this is 1, 2, 3, 4, 5, 6, right? And so L goes from 0 to n minus 1. Oh, I lied even about that. That is not true, right? You guys are saying, no, 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 this is 0, 1, 2, 3, 4, 5, right? Because S is when L equals 0 and it goes up, right? So n equals 1, L equals 0. So this is an S orbital. And that's all you can have. That's why they can only fit 2 electrons in there, right? If n equals 2 and L equals 1, then you could have an S or a P orbital. So you can put 2 electrons in that one, and you can put 6 electrons in that one, and so that makes a total of 8 electrons with an L equal to 1, right? And you keep going. Yes, you can put 6. I would make I'm saying that right. And then you have the magnetic spin number, which is the spot that it can be in. So it can be at negative L, 0, or positive L. So in an S, there's only a 0, right? And here, that's why you have a 0, 1, and then you'd have the other one would be negative 1, and the other one would be positive 1, right? And so forth. So it's a spot that it can be in. And then we have the spin quantum, so it either spins up or it spins down. Those are our choices. So when it's in the same spot, it's either up or down. So when you're writing it, you write it as the n orbital that it is. It's the n value, right? Because it's the first quantum number. And then the orbital type is S, so they don't usually write 0. So that would be L equals, so if it's S, remember that means L equals 0. I find that confusing. And then that's the number of electrons that are there, right? And then you can draw it like this. Just showing where things go. So in hydrogen, you only have one that's pointing up because that's all you can have. Hydrogen, you have one pointing up and one pointing down. Lithium, and it'll show energy levels, right? And so you saw that one problem where it had the levels and it showed energy as it was going up like this. So and it had little arrows to show you which way things went, and they kind of go in weird order sometimes. You're not expected to know which ones are a high energy state, but if they tell you, you should know that that's a higher energy state and it's excited. Like if this was over here, we'd know that was excited. Then we have the Pauli exclusion principle, which says that no 2 electrons in the same atom can have all the same 4 quantum numbers. So there'll be a couple questions like that you need to understand. So if n is 4, L is 1, that's okay, but m cannot be 2 because then it's bigger than L, so that's just not possible, right? If L is 1, remember, so this is the nth orbital, so it's just telling me what shell it is. L is sp, so that's a p orbital, right? And it's in the second lobe of the p orbital, and it's spinning down. That's basically what that says. So it's the 4th one, p2, et cetera, et cetera. So if you're trying to figure out the angular momentum in the quantum world, L is equal to L times L plus 1 times square root times h over 2 pi. So the h over 2 pi is the same, but now we see that it depends on L, right, and not on n. And I keep emphasizing that because that's what's important. That means when L equals 0 no matter which n it's in. So if we're in the S, then L equals 0, right? Kind of interesting, right? But that's because the s orbital is a circle, right? And so if here's my nucleus, and I've got this s orbital, no matter how big it is, here's the second one, there's always a probability that it could be in the center, and so therefore it has considered an angular momentum of 0 because it has a r of 0. If you're trying to figure out the number of electrons, because you can fit 2 in every of those spaces, plus the 2 you can fit in the 0th one because it was 0. So that's where you get the 2 is 2 times 2L plus 1. Of course, you have to know what the number for L is to be able to figure it out. So here's comparing Bohr versus quantum. So we said that Bohr is dependent upon n for its angular momentum. This is L's, right? L. And so quantum is dependent upon L. For Bohr, if you're in the nth orbital, L is the same, but L can be different for different n's because it depends on L. Yeah, I know, L, but that's angular momentum. That's the L for the orbital. And the orbits are circles, looks like a solar system, their probability in all different types of shapes. When we're talking about bremsstrahlung, that's when you take x-rays, right? And I have a sample, and the x-rays come in, and the x-rays come out, right? And so that's what you're looking at. The x-rays that goes in is the energy going in, basically based on the wavelength coming in, and this is the intensity of what comes out. And so certain ones are going to resonate and cause these peaks. So that is dependent upon the sample because it depends on how the sample's atoms act. But the energy, you always can get some of them just to bounce off, right? That have nothing to do with the sample, and that's what you see here. So if you're at a lower lambda, that means it's a higher energy. So if your potential difference is not big enough, right, is too small, then you might not have enough energy, right, to make it meet this point. And so let's say the highest energy x-rays I put in are over here, then I won't see those peaks. So that's what this is talking about, right? But it's only from the K shell. That was that first shell we saw. The peaks show unique electrons for the element, which are characteristics of x-rays, and the cutoff is the minimum energy, but it's independent of the material. It's just so that you can actually see whatever you see. And then to do it, you actually just bombard it. That's what we talked about. So this is the energy of the photon coming in, which is due to E times V, right? Because that is Q times delta V, which is Q times the potential difference, which is equal to, of course, kinetic energy, which is, of course, equal to work. And so if we solve that, then you end up with F is equal to EV over H, and lambda is equal to HC over EV. That is not electron volts. That is E times delta V. Right? Or Q times delta V. Yeah? And then we talked about lasers. I think we've all got that. They're monochromatic, in phase, and very high intensity. So the waves kind of bounce back and forth. They're all in phase, and out they come. Here are my two mirrors, and it's very high intensity. That's it.